Welcome to the engineering class for February the 1st. The first off, let's talk about some important announcements. Next week, Principal Wilson has scheduled a conference that all of us teachers are going to be attending. Some of your other teachers may have already mentioned this to you, and those that haven't will be mentioning it soon. It's my understanding that all Ames teachers are going to be attending this conference, and it goes Monday through Thursday. So what we need to do then is we need to come up with some activities that you can do by yourselves, just based on stuff that we put on Canvas for you to work on, without direct interaction from us all of next week. So with that in mind, I have changed the plan. Originally, I was thinking that I was going to have you guys work on your penny launching devices this week, and then next week we would do other stuff, but I'm going to switch it up. And the more I think about it, the more I'm thinking it's better to do this other stuff first rather than later. So this is a good thing, not a bad thing. All right, so I have looked over the engineering specifications that you had submitted as of yesterday. I see a few of you just gotten in this morning, right at the very last minute, so I haven't had a chance to look at those yet, but I have looked at most of them. And so I'd like to give you a little bit of feedback on those. And also I want to describe a change that I've decided to make based on what I saw when you wrote your functional specifications, and also based on this new plan with this conference next week that we all have to attend. Okay, so first off, let me give you the feedback. Many of you wrote excellent engineering specifications. Hang on a sec, we just got somebody who just showed up. Let me let him in. Okay, so the engineering specifications that many of you wrote were very good, very thorough, easy to understand. You had good drawings. Others of you, not so much. Some of your engineering specifications were pretty short on description, missing some important details, and a few of you didn't include a drawing. Most of you did, but some of your drawings weren't all that informative. So I am going to have you redo your engineering specifications, but before you get writing those, I'm also going to make a change in the requirement here. Up until now, I did not specify that you had, well, let me just tell you what I want you to do. Okay, so what I've decided I want you to do is that most of you have something that's basically a version of a catapult, right? So maybe you got some rubber bands where you pull the thing back and then release it, or maybe you've got a spring, or maybe some of you've got some sort of a long, thin slat, whether it's made out of wood or metal or what, who knows. But so then what you've done is you pull it back and then you let go of it, so that so that's where you get your energy from. So you've all come up with lots of different ideas, which I was very glad to see. But in pretty much all of the cases, what's happening is that your hand is pulling something back and then letting go, and then off it goes. And the more I think about that, the more I think that I want to do it slightly differently. So here is a new requirement that was not ever discussed before, but now effective today, it's in there. Okay, so I'm okay with you using your hand to pull something back or to bend something or whatever. So your hand is supplying the energy, and then the spring or whatever it is, the rubber band or whatever, that is storing the energy. Okay, and then when you let go, the spring or the rubber band is what propels the penny. But here's the new thing. I want there to be some sort of a catch mechanism, so that when your hand pulls it back and your hand adds energy into the spring, so you now have stored energy, I want it so that you can then release your hand, but the penny does not launch. I want there to be some sort of a catch mechanism that you pull it back and you cock it, okay, so that you can remove your hand and the penny will not launch. And so then in order to launch the penny, then there needs to be some sort of a release mechanism. And so then and only then the penny launches. All right. So this is a new requirement. And the reason that I'm doing this is because I want you guys to have experience with the concept of stored energy. That's something that mechanical engineers have to deal with a lot. And so first off, we are going to spend today talking about how much energy you need to store. We're going to spend today talking about how do you measure energy and how could you calculate how much energy the penny has to have in order to fly through the air to hit its target. And so we're actually going to come up with a number so that depending on how you design your device, you might need more energy or you might need less energy. So by the end of the day today, you should be able to come up with a number that tells you how much energy you need to store in the device. And then when we meet on Wednesday, we're going to talk about how to measure how much energy is stored in your device. We're not going to go on that today because I don't want to hit you with too much all at one time. So today the focus is simply on how to come up with a number that tells you how much energy needs to be stored in your device. Okay, so if you are using a spring, okay, so you're going to pull the spring back a certain distance, and so the more you pull it back, the more energy you have stored in the device. So by the end of the day today, you'll be able to calculate how much energy you need to have stored in the device once you pull it back. And then let's suppose that, I don't know, maybe we have some sort of a nail or something. Okay, so when we pull the spring back, okay, so let's say here's the nail, and I should have, okay, here's the nail, okay, all right. So what we do is we pull it back and we hook it on the nail, okay, and then we take our hand off. Try that again. So pull it back. Okay. All right. So then we can take our hand off, and we now have some stored energy in our device. We take our hand off and the penny does not launch, okay? And then in order to launch it, what we have to do is we then have to do something to release it. So maybe what we do is just give it a little bit of a nudge. And so as soon as we nudge up there, then boom, off it goes, okay? So the question is, how much energy do we need to store? Okay, so now, pretty much everybody has a device. Well, not just pretty much. I mean, absolutely everybody's device that I looked at, you are throwing the penny somehow. So the penny is traveling through the air. All right. So let's talk about what kind of energy does a moving object have, and how do you calculate? How could you put a number on what that is? Okay, so I know that some of you have had physics. And so let's see, Zaid, you're the one that I usually pick on, but let's give you a rest today. Let's pick on somebody else. How about, let's see, Austin, let's pick on you. Can you tell us how do you calculate how much energy a moving object has?
It's a 1/2 mv squared, right?
Okay. And what is the name that we give to that type of energy?
Kinetic energy.
Kinetic energy. All right. So I hope you all could hear that. His voice was a little bit soft. Maybe I just need to turn up my volume here. Okay. All right. So let me open up a whiteboard. Okay. So remember, first off, what is energy? We talked about this briefly the other day, but we didn't record it. At least I don't think we've recorded it. So before we do anything else, let's make sure we all know what energy is. So energy is defined as, so I'm going to put an equal sign with an extra line up above it. So you should all know that means that when you got three horizontal lines like that, that means is defined as. Okay. So energy is defined as the ability to do work. Okay. So what is work? Well, work means that you move some object. Okay. So if there's an object sitting there and you exert a force on it, then you have done work. And well, if it moves as a result of you exerting a force on it, you have done work. Okay, so if you have an object, so let's suppose I have this battery here, and I throw this battery at some object. When it hits the object, it's going to exert a force on that object, and if that object moves as a result of that, then we have done work on that object. So a moving object clearly has the ability to do work on some object that it might hit. Now, the more massive the object is, the more work it can do. Let's say I have this, I take this little battery here and I take this big motor here. If they are both traveling at the same speed, they hit some object, the thing that has more mass is going to be able to do more work. When it hits that object, it's going to move that object a lot further. Okay, so the more mass a moving object has, the more work it is capable of doing on some object that it might hit. Therefore, the more energy it has. So it's not surprising that the formula that Austin just gave us has an M in it. So that means if you increase the M, you've increased the energy. Now, also, the faster the moving object is going, the more it's going to be able to do. So, I mean, imagine that I've got some object here. So here comes this moving battery, it hits it and it pushes it a little bit. If I send it in at a higher speed, it's going to move it farther, right? So it can do more work. Now, most people assume that if you double the speed of this moving object, then that would double the amount of work that it would do. But it turns out it doesn't work like that. Scientists who've done experiments with this have found that if you double the speed of this object, when it hits, it actually can move the object 4 times as much as it could have at the old speed. And if you triple the speed, it ends up moving the object 9 times as much as it did compared to the old speed. All right, so the equation for the energy of a moving object, which, by the way, we have a name for that. We call it kinetic energy. The equation for kinetic energy is 1/2 mv squared. Now you might ask yourself, where does that 1/2 come from? And so I don't want to go into really detail here. Basically, when you take physics, you will learn. You'll learn where that 1/2 comes from. So for right now, let's just take it on faith, and let's take kinetic energy and let's abbreviate that as KE. All right, so this is an equation that physicists use all the time. And so what we need to do then is we need to calculate how much kinetic energy do we need to give to the penny so that it will fly through the air and hit the ground where we want it to hit. So we need to come up with a number for the kinetic energy of the penny, and that will tell us how much energy we need to store in our device. Okay, like let's suppose we do the math and we come out with the answer that in order for our penny to hit the target, we need to give it a kinetic energy of 12 whatever units that we use to measure energy in, which, by the way, let's see, most of you have not been in my physics class here. Okay, so Austin and Zaid, you are not allowed to answer. The rest of you, does anybody know what are the units we use to measure energy in?
Would it be newtons?
Nice guess, but no. Newtons is what we measure forces in.
Isn't it joules?
Joules, yes, joules is right. Okay, so let's suppose we do the math and we decide that in order for our penny to hit the target, it needs to have 12 joules worth of kinetic energy. Okay, so that means that in our device, if we're using a spring in our device, okay, so when we pull the spring back, we need to have 12 joules of energy stored in that spring. Okay. All right, so now let's play with the motion of the penny. When you look on canvas, you are going to see that I have added something into the canvas page that wasn't there before. You see this this new page here that says energy needed to shoot a projectile, and then this other one down here that says online simulator for projectile motion. So this projectile that we're talking about, that's the penny, the thing that flies through the air. For you guys, that's going to be the penny. All right, so let's look at this online simulator for projectile motion. So if you click on there, it'll take you to this page right here. And if we have an introduction, we have vectors, drag. Let's just look at the introduction for right now. All right, so what we have here is a cannon, and we can change the height of the tower that the cannon is sitting on. We can make it be any height we want. We can also change the angle that the cannon is pointed at. We can make it be any angle we want. We can also change the speed that the cannonball is moving at when it comes out of the cannon. And we can have that be anything from 0 up to 30. And by the way, we're going to be working in meters because when you're dealing with energy, the American system, you know, with feet and pounds and all that stuff, the American system really sucks big time when it comes to dealing with energy. And so even here in America, we use joules and newtons and meters and everything when we're talking about energy, because it's just so much better than the imperial system, which is the feet and pound system. Okay, so what we do is we pick some height at random, we pick some speed at random, we pick some angle at random, and then we shoot the ball and we see where it hits. And you see, oh my goodness, we missed completely, way too much. We gave that cannonball too much kinetic energy, okay? So what we can do is we can just change, we can give it less kinetic energy, shoot it again. Wow, hey, that was pretty good. That was just a guess. Now you can see I missed it by just I didn't hit the bullseye. I did hit the target, but not the bullseye. So let me take it down just one more step, shoot it again. Okay, so that one was not enough. This one here, that's the one I'm going to have to deal with because I can't go, it won't let me go 8.5. So I'm just going to have to say, all right, 9 is good enough. All right. So by changing the speed of the cannonball, which changes the kinetic energy, that changes where it's going to hit. Now, there are other things I could have done too. You know, what I could have done is I could have changed the angle. So let's say I shot there and I say, okay, well, that was too much. All right. So what I could do is I could just angle it down and shoot again. And bingo, I got it. Or interestingly enough, I could also angle it up. Okay. Now, when I angle it up, you notice that, hey, it went farther, and so that's bad. But if I go up far enough, okay, then it starts going down again. And so let's say I go to right here. Let's try that. Okay, and that's too low. So I can just kind of do trial and error until eventually I get it right. Whoops, almost. Let's come up just a little more. Let's see if I get it this time. Okay, yeah, I just barely got it. And now again, you see we got a bit of a problem. It'll let me go at 70 degrees or 75 degrees. And so 70 degrees isn't quite right. 75 degrees isn't quite right. What I want to go is I want to go somewhere in between, but it won't let me go somewhere in between. So what I can do then is I can, play with the speed a little bit, maybe try various things there. And bingo, got it. Okay. All right, so this is a really good thing for you guys to play with. And now, if you were in my physics class, I would make you do the calculations to calculate what speed you should be using and calculate what angle you should point it at. But since you're not in my physics class, I'll let you just do it by trial and error. So just kind of play around with this. So I want you guys, not right this minute, but after we break up today and everybody works on their own, I want you guys to play with this thing and just see how it works. And think that the cannonball here is actually going to be the penny that you guys are going to launch. So when you launch your penny, you've got the option that you could launch the penny so that when it leaves your device, it's going exactly horizontal. But if you want, you could also make it so that when it leaves your device, it goes at an angle. And now both of these tracks that you just saw, the penny was traveling at the same speed. But where it hit the ground was different because the angle was different. And of course, the starting height is going to make a big difference too. If you start from a lower height, you're going to see the ball doesn't go nearly as far. You start from a higher position, the ball goes farther, which is kind of a duh, of course, right? All right. So you guys need to make a lot of decisions when you are designing your penny launcher. And these are the details that you, for the most part, did not include in your engineering specification. And so this is what I want you to redo, not today. Your homework today is not to redo the engineering specification because you're not quite ready yet. But just be aware that when you redo your engineering specification, you need to tell me some things. One thing is you need to tell me what is the height that you have chosen that you are going to launch the penny from. Okay, are you going to launch it from basically sitting on the ground? If you're going to launch it from basically sitting on the ground, then you are going to have to launch it up at an angle. There's no choice there. But if you go up higher, then you don't necessarily have to launch at an angle. You could launch it horizontally if you want, or you could even launch it so it goes down at an angle if you want. And the higher you launch from, the less velocity you're going to need. Okay. So one of the things that you are going to have to include in your rewritten engineering specification is you need to pick a number for what is the height of your penny when it leaves the launcher device. Okay. You are also going to have to tell me what angle you want the penny to be moving at when it leaves the launching device. If it's horizontal, that would be an angle of 0. If it's anything above the horizon, that would be a positive angle. If it's anything below the horizon, that'd be a negative angle. Okay. And I want you to calculate what is the velocity of the penny when it leaves there. Okay, so now on the online simulator, you change the velocity just by moving the slider here. But in your thing, the velocity is going to be determined by how much energy you give the penny. And the energy is going to be determined by how much energy you store in your launcher device. So if you are using a spring, okay, then if you pull this back a little bit, then you've only stored a little bit of energy. And if that's not enough, then you have to pull it back more. And so that will give you more stored energy. Okay. Now, if you're using rubber bands, then maybe if you use one rubber band, you might find that that's not enough energy. So then you need to use maybe 2 or 3 or 4 rubber bands. Okay. So now, here comes the important thing. Let's calculate a number for how much energy the penny needs based on certain assumptions. Okay. Now, if we include the angle as one of our variables, then the calculations get much more complicated. Now, those of you that have had physics, you should be able to do the calculations, okay? But most of you haven't had physics. So I recommend let's keep the calculations relatively simple. And let's see if we can calculate how much velocity is needed. Because once we know the velocity, then we know that the energy is 1/2 mv squared. So if we know the mass of a penny and we know the velocity, then we can calculate how much energy we need to store in our device to work it. Okay, so like for instance, let's suppose that we just do some trial and error here. And by the way, we can move this target wherever we want. So for you guys, the target is going to be 5 feet away. But for right now, let's just pick some other thing. Let's say that we want the target to be 10 meters away. Okay, so I'm going to put it right there. Oops. Okay. So in fact, let me zoom in a little bit here. Okay, you see that? So the target here is 10 meters away. And now let's pick some starting height. So Eliza, give me a number somewhere between 3 and 9 for what you'd like the starting height to be.
Let's do 6.
Say it louder.
6.
6. Okay, so Eliza wants her starting height to be 6 meters. Okay, so those of you that have had physics, you could actually calculate what the velocity needs to be in order to hit the target. Now, the rest of you, you haven't had physics, and I don't want to take the time to teach you physics, so I will let you do this by trial and error. So let's just pick some speed at random. You know, let's say 20, just a guess. Let's try shooting it. Whoa, that was way too much. Okay, so let's bring it down. Let's try 10. Oh, that's pretty good. We hit the target, not necessarily the bullseye. Let's bring it down by 1 more. Now we can only go in 1 increment here. Okay, let's take it down to 9. Let's see how that works. Oh, wow, right in the bullseye. Yay. Okay, so through trial and error, we have decided that the velocity that we need is this number right here. So 9 meters per second. Now notice we're not working in feet here. We're working in meters, which you need to do. Okay, so let's suppose that this was our penny. And so we've determined using this online simulator that the velocity that we need our penny to have is 9 meters per second. So now the question becomes, how much energy does that correspond to? All right, so Austin told us that the kinetic energy was given by 1/2 mv squared. So if we knew what the mass of the penny was, we could just stick that in here for m. And now experimentally we've determined that v needs to be 9. So we could then calculate how much energy we need the penny to have, and that is how much energy our device needs to store. You see how this works? Okay, so if you go and look up the mass of a penny, you'll find out that the mass of a penny is 2.5 grams. Now, a gram is not a standard physics unit. Those of you that are taking chemistry, you're saying, wait a minute, the gram is the standard unit that we use in chemistry. Yeah, that's one thing where chemists and physicists, for some reason, they never got together on this. And it's really a shame that they didn't. But when we're working with physics equations, which is what engineers do, we cannot use the gram. We have to use the kilogram. So this is actually a good experience for you guys. You guys need to be really good at converting units. Okay, so we need to know how many grams equals how many kilograms. Anybody remember off the top of your head how many grams equals a kilogram?
That's 1,000.
Very good. So 1,000 grams equals 1 kilogram. So what we need to do is we need to convert 2.5. So what we're going to do is we're going to take 2.5 grams, and we're going to use the Ames method for unit conversion. So we're going to use parentheses and a horizontal line. And then one of these guys goes on top and one goes on bottom. So if we want grams to cancel out, then we need to put this guy on the bottom. So we put 1,000 grams on the bottom, and the other guy, we put him up on the top, 1 kilogram. So when we multiply by 1 kilogram divided by 1,000 grams, well, 1 kilogram is equal to 1,000 grams. So basically we're multiplying by 1, which means we're not changing anything, but the units change. So that gram cancels that gram. So what we've got is 2.5 divided by 1,000. So that means that the mass of our penny is 0.0025 kilograms. That is the number that we need to plug in for M. M has to be in kilograms, cannot be in grams. Okay, so I would like everybody to please get out your calculators and tell me how much energy does this correspond to? And type it in the chat box using a private message so that nobody else can see your answer, only I can see your answer. Give me a number. How many joules of energy do we need our penny to have if we want it to be moving at 9 meters per second? You guys don't have your calculators handy? You should always have a calculator sitting by your side when you come to this class. Now you can use your phones. I'm okay with that. Guys, okay, now starting to see some numbers. Okay, good. The numbers that I'm seeing are, ooh, they were the same. That last one was different. Oh, okay. Yeah, I'm starting to see different numbers. Okay, so maybe I better do it too. All right, so I'm going to get out my calculator. So 1/2 times the mass of the penny, which is 0.0025, times the velocity squared, so times 9 squared. Okay, so what I get the kinetic energy to be 0.10125, which is what most of you got. Okay. All right. Now, some of you rounded that number off, which is good because we do need to round off. And so let's see what's an appropriate thing to round it off for. So most of you by now, you know the rules for rounding off is you look at how many sig figs, how many significant figures does each of your input numbers have. So this guy here has 2 significant figures. Now the velocity only has 1, but I'm thinking let's pretend that it has more than just 1 sig fig because we should be able to measure it better than that. So let's pretend that we know that the velocity is actually 9.0. So that means that that number also has 2 significant figures in it. Okay, so if both of our input numbers have 2 significant figures, then that means our output number should also have 2 significant figures. So we need to either round it up to 0.11 or we need to round it down to 0.10. And hopefully you see, well, obviously this guy is closer to that lower number than he is to the upper number. So 0.10 is the answer that we need. Okay, so what we've just done is we've figured out that the kinetic energy that we need to give to our penny is 0.10 joules. So what that means then is that when we take our device and we pull back the spring, we need to pull it back so that the energy stored in this spring is 0.10 joules, because that will then give 0.10 joules of kinetic energy to the penny. Okay. Now, I'm not going to do this today, but next time we meet, we're going to calculate how far back do you have to pull it in order for it to have 0.10 joules of kinetic energy. We're not going to do that today. Today, we're just going to focus only on how much energy does the penny need to have. Okay, so you guys good with that? All right, so now in your homework tonight, I'm going to ask you to calculate how much kinetic energy the penny needs to have for various conditions. So let's go back in here to our simulator again. All right, so we just calculated is that if, let me turn on annotation here. So if the height is 6 meters, then the kinetic energy needs to be 0.10 joules. What if we go with a different height? Okay. What if we go with a lower height? So instead of 6 meters, let's take it down to 3 meters. Okay. Now I want you guys to type into the chat box and tell me, what do you think does, in order to hit the target, do we need to give it more kinetic energy than we did before, or do we need to give it less kinetic energy than we did before? So I want you guys to type in the chat box, and I want you to say either more or less. Okay, so interesting. Okay, some of you are putting question marks on your answer. Okay, so what I'm seeing is roughly half and half. Actually, a few more of you are saying more, but it's pretty close to half and half. All right, well, let's find out what it is. And again, those of you that know physics, you could actually do the calculations, but since most of you haven't had physics, let's just do it by trial and error. Okay, so I'm going to keep the speed the same as it was before. It was 9 meters per second before. In fact, let's make a note of that. Okay, so the speed had to be 9 meters per second before. So this over here, this is all before. Okay, so if I keep the speed the same at 9 meters per second, let's see if it hits the target. All right, let's go ahead and launch it. And boom, you can see it did not hit the target. So if we are launching the penny from a lower height, that means we need to give the penny more energy. Otherwise, it's not going to hit the target. All right, so how much more? Well, let's just do it by trial and error. Let's try that one. Whoops, that was too much. Come back a little bit. Okay, still too much. Come back a little bit more. We hit the target, but not the bullseye. Let's come back a little bit more. And okay, good. That's as close as we're going to get. Okay, so that means our new speed now. Whoops, sorry, I didn't mean to do that. I keep forgetting that before I touch my screen, I have to turn my annotation back on. Okay, so our new speed is now 13 meters per second. Okay, meters per second. Okay, so that means if we go down to a lower height there, we need to give the penny more speed, which means we need to give it more kinetic energy. Okay, now let's have you guys all, let's practice again. So I want you to tell me how many joules of energy do we need to give it then? Remember the number for mass, just in case you've forgotten. The mass of a penny is 0.0025. And remember that the formula for kinetic energy is 1/2 mv squared. Okay, so let's see what you guys come up with. How many joules of kinetic energy do we need to give it now at our new height? So as before, please type it in the chat box in a private message, not a public message. Okay, good. I'm starting. Whoa, we were seeing the same answer until one of you was a little bit off. So it looks like everybody except for one of you is getting 0.21. Whoops. Oh, now, okay, that's now one of you. Okay. So almost all of you are getting that the kinetic energy works out to be 0.21 joules. Let me make sure that I agree, because a few of you got a different answer. So 1/2 times 0.0025 times our new velocity, which is 13 squared. Okay, yeah, I'm getting 0.21 also, just like you are. So actually I'm getting 0.21125, but if I'm only allowed 2 sig figs, then I need to either round it down to 0.21 or round it up to 0.22. And clearly you can see this number rounds down, not up. Okay, so 0.21 is it. By the way, rounding off numbers is a very important skill that you guys need to know. Okay. Now, what if the distance is not what we've just done here? So this distance that we've been playing with up until now, okay, our distance here was 10 meters. Well, for you guys, that's not the right distance. For you guys, the distance for the target is 5 feet. So we need to work in meters. So we're going to have to calculate how many meters is 5 feet equal to. So we're going to need a conversion factor. Now, this is one that most people don't have memorized, but so I'll just go ahead and tell you. So 1 meter is equal to 3.28 feet. Okay, so I want you guys to do the math real quick and then type into the chat box. So how many meters is this? Okay, what number do I have to write in here for that? How many meters is 5 feet equal to? Okay, I'm seeing one answer. Let's see a couple more. Okay, good. All right. A couple more, just to be, oh, okay, there was a different one. Ouch. Okay, so almost everybody's in agreement here, but one of you got a different answer. Okay, so remember the Ames method for unit conversions. So 5 feet, and then we write parentheses in a horizontal line. So one of these guys goes on top and one of them goes on bottom. How do you know which one goes where? Most of you got it right, but a couple of you didn't. Okay, how do you know which one goes on top and which one goes on bottom? Well, 5 feet is the same thing as 5/1. So we got feet on top. If we want feet to cancel out, that means feet needs to go on the bottom. That means 3.28 feet. That has to go on the bottom. That's the only way we're going to have feet cancel feet. So if that goes on the bottom, then 1 meter goes on the top. So the answer is 5 divided by 3.28. Okay, so the answer then is 1.52 meters. So 5 feet is equal to 1.52 meters. So what we need to do then is we need to take our nifty little simulator here and we need to move the target so it's 1.52 meters. And you'll see that it doesn't work very well. When it gets inside here, it's really hard to deal with. You can't even see it. So, I mean, here's 3 meters right there. It's 1.5 is in there. So rats. Our online simulator is not going to be good for what we want. It can't handle a target that's close. So we're going to need to use some physics. Now, since I realize that most of you haven't yet had physics, I did the physics for you. All right, so if you click on modules, then you come back here. So this is your homework assignment for tonight, energy needed to shoot a projectile. So if you click on this, and then let me go to preview, because remember the teacher version looks a little different than the student version. So if I click on preview, then it'll look more like what you guys will actually see when you do it. So you'll notice that I've given you the equation for kinetic energy, right? And I've talked about the fact that the units for energy are joules. And I've talked a little bit here about why it is that we use the metric system, even though some people, like for instance, the people on Fox News, they consider the metric system to be commie units. And by the way, have we got time? Yeah, we got time. Tell you what, I'm going to play this little video. I mean, Fox News is an astoundingly stupid organization. Now, if any of your parents like Fox News, you might think that I need to apologize for that, but I am not going to apologize for calling Fox News stupid. And this video right here is the perfect example for why that is. So let me play this little video. This is a real honest to goodness video that Fox News put a couple years ago talking about the metric system. Everybody, if you want a good laugh, watch this video. So here it goes.
Almost every nation on earth has fallen under the yoke of tyranny, the metric system. From Beijing to Buenos Aires, from Lusaka to London, the people of the world have been forced to measure their environment in millimeters and kilograms.
Did you
The
see
United
the
States
look
is
on
the
his
only
face?
major country that has resisted, but we have no reason to be ashamed for using feet and pounds. So says New Criterion editor James Panaro. We spoke with him recently.
I'm joining you tonight as an anti-metrite. I'm taking a stand against the metric system, the original system of global revolution and new world orders.
God bless you. That's exactly what it is. Esperanto.
So it goes on, but I'm going to stop it there. But this is real. Fox News honestly published this thing saying that the metric system was invented by communists, and America we're the one and only country that's standing up against this commie system of the metric system. It's hilarious. Fox News is just astoundingly stupid. So anyway, we are going to be using the metric system because it is a better system, and especially if you're working with energy. Even here in America, the imperial system, it just falls to pieces if you try to do energy calculations. You have to use the metric system. Okay, so in your homework tonight, I ask you a bunch of questions where I tell you the mass and the speed and ask you to calculate kinetic energy. All these first ones should be really easy. Everything that we've done so far, you should have no trouble doing these first ones. Okay, now, here is the important new stuff. What I've done is I have done the physics for you that shows you this. Okay, so you don't need to use the online simulator. You can just use this equation right here. As long as you're using the metric system, so that you're measuring the height in meters and you're measuring the distance that the penny flies in meters, as long as you're working in meters, then the velocity that you need to give to the penny, if the distance is 5 feet, which corresponds to 1.52 meters, as long as this distance is 1.52 meters, okay, then this is the equation that you can use that will tell you how fast the penny needs to be moving when it leaves the launcher if the penny is launched horizontally. That's crucially important. If you launch your penny at an angle, then this equation does not work. Okay. This equation only works if you're launching the penny horizontally. And in the homework tonight, we're going to make that simplifying assumption. Now, those of you that have had physics, if you want to do it the more challenging way, then you have my blessing to do it that way. But for the rest of you, let's keep it simple. Let's assume that we're launching the penny horizontally. So as long as that's the case, this equation will work. Okay, so let's do another exercise. Get out those calculators. Luke, give me a starting height for what you want the penny to start from. Give me a number, any number at all.
2 meters.
Okay, so Luke wants his starting height to be 2 meters above the ground. All right, so I want everybody to calculate what does the velocity need to be in order for it to hit the target. Okay, and again, type your answer into the chat box using a private message, not a public message. Okay, I'm seeing an answer, but only one so far. Okay, now I'm seeing 2 answers, 3. Okay, good. All right, all of the answers that I'm seeing are the same. Okay, good. I'm reassured. Okay, so I'll trust you then. All right. So you guys have all told me that if you're starting from 2 meters above the ground, then the velocity that penny needs to have is 2.38 meters per second. If it's anything faster than that, then the penny is going to overshoot the target. If it's anything less than that, then the penny is going to fall short of the target. So this is the magic velocity that we need the penny to have. Okay, next question. How much kinetic energy does that correspond to? So remember what the mass of a penny is, right? The mass of a penny is 0.0025 kilograms. Okay, so now I want you guys to do the calculations, and I want you to tell me how much kinetic energy does that correspond to? And type it in the chat box using a private message. Okay, I'm seeing 1 answer, 2 answers, and use 2 sig figs, please. And by the way, yeah, well, okay, so give me answer using 2 significant figures. Okay. I need some more answers. 2 sig figs, not 1, please, 2 sig figs. Okay, good. I need to see a few more. Some of you guys aren't there. Are you asleep? Okay, I'm starting to see more answers now. And now some of you are saying that the answer is 0.0071. Others of you are saying that the answer is 0.0070. So maybe I better do this one myself. Okay, so kinetic energy is 1/2 mv squared. So 1/2 times m, which is 0.0025, times v. Now I'm going to use this number for v, which has 3 sig figs. Even though we know that our final answer is only allowed 2 sig figs, you don't want to round off your answer too early. This guy right here is just an intermediate answer. You want to keep at least 1 extra sig fig in your answer. So I'm going to type in 2.38 squared. I'm not going to type in 2.4 squared. Okay, so when I do that, I get that my calculator says that the answer I need is, or the kinetic energy works out to be 0.00708. Okay, so if I round that off to 2 sig figs, I've got to either round it up to 0.0071 or round it down to 0.0070. So hopefully you can see that the 8 here, this is more than halfway between the two. So that means I'm going to round it up. So the answer that I need to put into to Canvas here is 0.0071, not 0.0070. Now Canvas is going to be very picky about this. when you guys put your answers into Canvas for these homework problems, if you put in 0.00, I mean, if this was the question, if you put in 0.0070, even though that's really, really close to the right answer, it's not the right answer. Canvas is going to mark it wrong. So an important part of being an engineer is knowing how to calculate things correctly with the right number of sig figs and round it off the right way. Okay, so now that we know how to do that, so if you scroll down, you're going to see that basically what I've done here is I've just picked a couple heights, and I've always assumed that the launch angle is 0, because otherwise this equation that I gave you up here does not work. This equation only works if the launch angle is 0. So in all of these problems that you have down here, we're always going to assume that the launch angle is 0. Now, when you guys make your actual devices, your launch angle doesn't have to be 0. It might be something different. Okay, but basically that's it. Okay, so that is your homework tonight. Is basically just use the formula that I gave you in order to calculate what does the velocity of the penny need to be depending on what starting height you've chosen. And then you need to convert that to tell me how many joules of kinetic energy that works out to be. And that's all we're going to do for tonight. Now, next time we meet, we're going to learn how to take a spring, and we're going to learn how to calculate how far back do you have to stretch the string in order to have a certain amount of stored energy in the spring. We're not going to go into that today because that's going to be too much. Today is just we're going to calculate how much energy do you need. So is that straightforward, guys? Could you think you could do that if I turn you loose right now? So give me a yes or an okay or a thumbs up. Okay, that works too. Okay, so I'm seeing lots of thumbs up. Okay, great. So we have, let's see, oh my goodness, we've got about 18 minutes left in class before the bell rings. So I'm going to turn you loose and let you work on the homework assignment. And if you use your time effectively, hopefully you can get it done before the bell rings, then you won't have any homework tonight. So if you don't have any questions, I will let you go ahead and type by in the chat box, and I will see you next Wednesday. Okay, see you later. Moses, do you have a question? Nope, apparently not. Okay. All right, I'll end the class.